Once again, this is the program, and last week we discussed the first 4 points. So we went from inferring one parameter to inferring many parameters. In particular, we discussed the problem of inferring the principal component of a matrix. And now, for the last part, this week I would like to discuss the last point, which is about network inference, so inferring a network of interactions between variables. And so to explain what I mean, let me give again the example of Gaussian variables. So we will consider what are called graphical models in general. And for the specific case of Gaussian variables, we will go back to the same distribution of multivariate Gaussians, where the probability of your data, given a certain matrix T, is given by a normalization that now I call Z, times the exponential of minus y transpose times T times y. Okay, where again y is a vector of L dimensions. These are our data. So L is the length of our strings of data. The normalization Z of T is given by 2 pi over L over 2 divided by the square root of the determinant of T. And T is a L by L symmetric and positive definite matrix.
I have 2 questions. The first one is graphical. Do you mean graphs or plots?
I will.
Okay. Second, can you summarize again a little bit what will be the focus and the main points of the lecture?
Yeah, that's what I'm going to do. So ask me again in 3 minutes if you don't, if I don't answer. So exactly, what do we want to do? So we have already discussed the problem of inferring the matrix T, but now we would like to go a bit deeper into this problem and try to understand what happens if the matrix T is not a dense matrix, but it is a sparse matrix. Okay, so let's say I generate the data with a certain matrix T hat, and this matrix T hat has elements ij, but I suspect that not all elements are different from 0. I suspect that there are maybe many elements that are 0. Okay, why? So this defines a graph, and that's why I call it a graphical model, because the graph will be the set of edges between, the vertices of the graph are the L sides that correspond to the coordinates of y, and the edges will be the pairs ij such that Tij is non-zero. And I would like to understand or to infer the properties of this graph. So where are the non-zero components of T? Why am I interested in this? So remember that the correlation between variables is the integral of P of y times yi yj. I'm assuming 0 mean, so this is the correlation. And this is given by the inverse of T. So of course, if T is sparse, C doesn't need to be, is not sparse in general, okay? So you can have a situation where, for example, you have done statistical physics. You can have, for example, a 2-dimensional easy model where the network of the interactions is very sparse. Each spin all interacts with the 4 neighbors, but the correlations can be very long range, right? So in principle, from the data, we can access things like the correlations, and we would like to reconstruct the network of interactions from this. in particular, we are interested in the network of interactions because we can consider the conditional probability. So we take one variable, yi, and we can consider the conditional probability of this variable when we fix all the other variables. So I will call y minus I the set of all the other variables except I. So if I fix all the other variables except one and I look to the conditional probability, from here you can see that this is going to be proportional to the exponential of minus t I over 2 times yi minus the sum over j different from I of t ij yj divided by t I square. Okay? If you take, here you have a sum over ij of yi t ij yj, so you can write it in this way, and then you have to normalize it. So you see this is a Gaussian. It is a Gaussian that now has a mean. This is the mean. So if you fix the yi, the yj, sorry, if you fix the yj different from I, then yi will have a certain mean that is given by this quantity, and then it has a variance that is 1 over t hat I. So the normalization is going to be simply square root of t I divided by 2 pi. So you see that, of course, if tij is equal to 0, then the conditional probability of yi does not depend on yj. So this is why we are particularly interested in reconstructing the graph, because once we have a graph, we know that a certain variable conditioned to the rest will only depend on a subset of the rest of the variables that are those defined by the graph. Okay? So we would like to reconstruct this. And of course, so if tij is equal to 0, then yi is conditionally independent of yj, but it could still be correlated. So yi and yj can still be correlated because maybe they are both conditionally dependent on a third variable, which is the famous statement that correlation is not causation, right? So conditional independent, the conditional probability is really a measure of the direct direct interaction between variables, while correlation can be a measure of any kind of other correlations that you have in your system of variables. So the goal now is going to, the goal is to reconstruct this matrix as precisely as possible, in particular find the non-zero entries, in such a way that we can reconstruct the network of interactions in our system. And then the goal will be to use this to model proteins. In particular, we will see that in proteins, the interactions that are non-zero give you information on the structure of the protein, so how the protein folds in 3 dimensions. Did I answer to your questions? Okay.
I need 2 repetitions, please. The first one is, can you repeat, can you explain again the formula of the matrix Cij?
This one?
Yes. How can we get the inverse of the sparse matrix?
Ah, okay. I didn't.
Can you repeat the discussion about the conditional probability independence with the relation to the correlation instead?
Yes. So, okay, this formula, I didn't derive it. There are many ways of deriving it. It's basically Gaussian integrals. One possibility is to use the fact that the correlation is the derivative of the logarithm of z with respect to tij, right? Because this is a Boltzmann factor. So if you take the derivative with respect to tij, it will bring down yi, yj, okay? So you can write that essentially Cij is the derivative with respect to Tij of the logarithm of z, which is the usual, say, the thing that we discussed when we did maximum entropy, right? So whenever you have an exponential distribution, you have this kind of thing, because this is basically 1 over z times the derivative of z, and z is the integral of this. So when you take the derivative, you bring down yi, yj, okay? So then you have to do the derivative of 1/2 log that t, and then you have to work out the fact that this derivative is basically tij minus 1, which is a little bit of calculation. Maybe I mean, I would not do that. And the correlation, and this is the correlation matrix, yes. Now, the other point is, what I was trying to say is that if you really want to know, like whether there is a direct interaction, let's call it, between two variables, you should look at the conditional probability. The conditional probability tells you if you fix a certain variable, do you have an effect on the ones that on the one that you're looking at, right? So, for example, if you have a two-dimensional easy model, if you fix this 4, then this one is only. I mean, the rest of the system does not have any influence on this one if you fix this 4. So this defines really the direct neighbors of the. So the non-zero elements of T tell you who is interacting with who. The correlations can be. So this spin can be correlated with a very far away spin, because this spin is interacting with this one, that is interacting with this one, and then you have a chain of interactions. Or two variables can be correlated. For example, you can think that these two are correlated because they are both interacting with this one that is in between. So you can have all. I mean, correlations can come from chains of interactions, even if you don't have any direct interaction between two variables. Okay? Which is, yeah, the typical example that, I mean, correlation is not causation. Is you can have something that is the cause of two things that are independent, conditional to the cause, so they are not interacting, but they're both, I mean, they are both correlated to the same third thing, and then you get the correlation. Okay, I hope I was clear. Now, okay, so the goal is to reconstruct this T. Now, I already told you before that the one way to infer T is to say, okay, let's erase this. I can do maximum likelihood once I have my data. So let's assume I have many data generated from the. Let's assume I have many data generated from T hat. I have M data. So what I can do, I can compute the likelihood. I can assume that I know the model, but I don't know T. So the data have been generated with T hat, but I don't know T hat. But I know the likelihood. So I can compute the likelihood of my data, which will be, because the data are generated independently, the probability of the data is the product of the probabilities, and so the likelihood, the log likelihood is the sum of the logs. And this is what? This is, if I plug this here, I get minus 1 over m sum over m of yim tij yjm minus log z. And then this term gives me 1/2 logarithm of the determinant of T plus constants that I drop. And this term gives me minus, sorry, here there is a sum over ij. This gives me sum, and there is a 1/2 as well that I didn't put, sorry. There was a 1/2 here that I forgot. So I get 1/2 sum over ij of tij Cij, where Cij is the empirical correlation of my data. And so this is also minus 1/2. Let me write it here. This is minus 1/2 trace of T times C. Okay, so if I maximize this likelihood, this is a convex, this is a concave function. The free energy is a convex function, and this is a concave function. The second derivative of this thing is negative. You can check it explicitly by writing the matrix in a proper way. You can check in the book, there is the discussion. But you can also, I mean, you know it from the fact that this term is linear, so when you do the second derivative, it will disappear with respect to t. And this term is again the logarithm of the partition function. So if you do two derivatives, it will give you a variance. So this will be minus a variance, and so all the second derivatives of the likelihood are going to be negative. So this is a concave function, so it has a unique maximum. And the maximum is obtained by taking the derivative. And when you take the derivative, again, you use this formula that I didn't prove, that the derivative of log that t is the inverse of t. And here you get just minus c. So our estimator is going to be t star ij equal to c minus 1 ij. We already did this last week, right? So
no, sorry. But if Cij is t to the minus 1, we get 0.
yes. So sorry. We want to estimate t by maximizing the likelihood. So what I have to do, I know that my data have been generated by some ground truth t hat. I know that this is the likelihood, but I don't know t. So I compute the likelihood as a function of t. I get this. And then I know that this has a maximum, unique maximum. So to find the maximum, I take the derivative and I set it to 0. And then the derivative gives me t minus 1 equals c.
Yeah, so we discovered the definition by the maximum principle.
Yes, exactly. So the maximum likelihood tells you that, well, what you have to do is, so the true t hat is the inverse of the true matrix. You don't know the true matrix, but the best you can do is to take the empirical matrix and invert it. Okay? Okay. So we had already done this last week. Now let's see a bit better what happens. The problem is, yes?
Can you please repeat why in the first place you assume that the likelihood is a Gaussian function?
I don't know, this is just to do I'm discussing the simplest case. Then later we will do other models. But for the moment, let's just to give a bit of intuition of what will happen. Let's consider the simplest case. The simplest case is Gaussian, where in the Gaussian case I can compute everything explicitly. So I just do that, and then later we will consider different kind of.
The likelihood is just our model. We choose
Yes, yes. So if you have real data, and you know, as we did in the tutorials, if you have real data, you can remove the mean and normalize by the variance, so you get variables that have 0 mean. You can assume they are Gaussian. This is our model of the data. Now I'm assuming that not only this is our model, but it's the correct model. So the data have been generated by a Gaussian, and we know that it's a Gaussian, so we use a Gaussian. In concrete applications, you don't know the model, so you have to guess.
So, for example, it's possible that it is wrong.
Yes, of course. Yes, yes. So maybe you have data that are not generated by a Gaussian, and you say, okay, let's try a Gaussian, and you get an approximation of your probability distribution that is of this form, but it's maybe not the right one. So when you have data, well, you have to make a guess.
Can change our model again?
Sure. Yeah, we can improve the model in various ways. We will discuss that later. Okay. Now, the problem is we we would like to know which are the non-zero elements of T hat, but we know that we have seen last week that Cij, which is the empirical correlation computed from M data, is given by C hat when M goes to infinity. So if I have infinite data, this will coincide with C hat, and my estimator will coincide with the true one, so everything is fine. But if I have finite data, in general, I will have a correction. I mean, at the leading order in large M, I will have a square root of M correction, because this is an average over M points, and by central limit theorem, this will converge to the average, but with fluctuations, and the fluctuations are going to be given by a Gaussian variable divided by square root of M. So the problem is that now, because of this, even if M is large enough, but not infinite, essentially all the matrix elements of C are going to be non-zero, even if C hat. So when you invert your matrix, because of this noise, you are going to get a dense matrix T star, and it's not clear that you can decide where are the real interactions and where is the noise. Okay, so we would like to understand if we can clean up a little bit this noise. So there are many techniques to regularize the problem, to get rid of the noise. And I will not discuss all of them. I will give you now an example, and then I will give you other examples when we go to non-Gaussian variables. So the simplest thing you can do to regularize the problem a little bit is to say, okay, I add some penalty to the non-zero elements of T. So I say, okay, I will take my likelihood, and then I put some penalty for non-zero T. How do you put this penalty? As we did last week, you can put an L1 norm. So you sum a constant gamma times the sum of the absolute values of Tij. Why? Why L1? L1 is a good choice, usually, because then this equation becomes, when you take the derivative, you get the same, and then this term gives you minus gamma times the sine of Tij. This has the good property that it's still convex. I mean, it has a discontinuity in T equal to 0, but it's still concave. Actually, there is a minus, so you add this is concave, and you add the concave thing, so it still has a unique maximum, and it will basically it gives you this penalty when T is non-zero. Now, if you could say, okay, I can put a different power. So, for example, you can put what is called L2, where you put a square here. But if you put a square, this gives you a linear term here, which is small when T is small. So it's not giving a strong penalty to non-zero values. Okay, so L1 is usually considered to be a good choice if you want something sparse, because the penalty is linear at small t, so it's strong. If you put a lower power, in principle it's better, but then you can lose the convexity and things can become more complicated. So L1 is considered as a good choice. I'm not going to motivate it too much, because I actually don't think it's the best choice. I will show you something better later on, but it's a choice that is very common. So let's see what happens if you put this L1 regularization. So what happens to the matrix elements? So this derivative has this form when t, if you look at this thing as a function of tij, here I put dl over dtij. So first of all, if gamma goes to infinity, I can erase this. If gamma goes to infinity, then of course here I'm putting an infinite penalty for any non-zero t. I forgot to say, here I don't put a regularization for the diagonal terms, because the diagonal terms of c are equal to 1, because I'm normalizing the variance of the y's to 1. So maybe I assume that the y's have been normalized in such a way that the variance of the y is 1. So I don't put a penalty for the diagonal elements. I only put a penalty for the off-diagonals that are the ones that give me interactions. And here is I smaller than j because tij is symmetric. So when gamma goes to infinity, all the off-diagonal elements of t go to 0 because of this. And so t is going to be diagonal. And so it's going to be delta ij times the diagonal elements, and the diagonal elements are given by here when I is equal to j, I don't have this, and here I get just tii equal to the inverse of cii, which is 1, so this will be delta ij. So if I put an infinite regularization, my estimator that maximizes this likelihood is just the identity, which is, by construction, is correct. So if I kill all the off-diagonal elements, I will conclude that my Gaussians are independent, they have 0 mean and unit variance, and t is the identity. So now let's look at this equation. Now I put a finite gamma, but I assume that gamma is large enough that t is close to the identity. So what happens here? Well, t minus 1, if t is the identity, t minus 1 is the identity. So for the off-diagonal terms, here now let's put I different from j. For the off-diagonal terms, this term is not there. So the derivative is going to be just minus 1/2 cij minus gamma times the sine of t. So you get something like, for example, if c is positive, you get, when t is positive, you get minus gamma minus something positive. So you get something like this. And then this is for small t. Okay, then it can be nonlinear. And when t is negative, this is minus. So you get plus gamma minus something. So you get something like this. So this will be minus c over 2 plus gamma, and this will be minus c over 2 minus gamma, right? So as long as you are in this situation, t equal to 0 is the solution. Because if you put t a bit bigger than 0, the derivative is negative and you go back. And if you put, it's discontinuous, so it's a bit ill-defined, but the maximum, there will be a cusp of the function L, and the cusp will be in t equal to 0. But then when you increase c, so this is the case when absolute value of cij, and sorry, I also should correct one thing. There is it's a minor point, but if you do this way, you are treating tij as the independent variable for I smaller than j, because tji should be equal to tij. So then when you do this derivative here, the 1/2 actually goes away. Because if you enforce the symmetry of tij, you have two terms, one for tij and the other for tji. Anyway, it's a factor 2, it doesn't change. So actually this factor 2 is not there in this convention. Sorry for the confusion. So as long as cij absolute value is smaller than gamma, then the identity is still the maximum. So the conclusion is that if gamma, if you regularize your problem by an L1 norm, if gamma is bigger than the maximum over I and j of the norm of Cij, then this is still the solution. So let's say, maybe let's write it better. We get that Tij is equal to delta ij for any gamma bigger than the maximum over I smaller than j of Cij. Okay? Because if gamma is bigger than the maximum of all the possible correlations, for any matrix element Tij, you are in this situation. Okay, now you decrease gamma, so you start with very large gamma, your matrix is the identity, now you reduce gamma progressively. At some point, you hit the maximum Cij. The Cij is fixed, is given by your data, right? Cij is 1 over m times the sum over m of yim yjm. So this is your empirical correlation that is given. So you reduce gamma. At some point, for example, if you reduce gamma and C is positive, Cij is positive, this will go down until at some point you go to this situation, right? When gamma is small enough. So one of the matrix element of T, of diagonal matrix element, becomes non-zero, okay? And it will be 1, because you can check that for all the others, they will stay 0. So there will be, at gamma 1 equal to the max of Cij, you have one non-zero Tij. Okay, and then you can keep reducing gamma, and you can show, I will not do it, but what happens is that basically the Tij will appear continuously at these transitions. So they will pop out of 0 one by one. And if you check the book, there is an example with a 3 by 3 matrix. You can play with it. You can take a small matrix. You reduce gamma, and you can follow. So they will be at gamma 2, which will be the second smallest matrix element. You have 2 non-zero, and so on and so forth. So if you plot, basically, if you plot the matrix elements Tij as a function of gamma, for large enough gamma, they are all 0. Then there is gamma 1, and you start to have a non-zero element. Then at some point, there is a gamma 2, and there is another non-zero element. And then there is a gamma 3, and there is another element, and so on and so forth. Okay? So if you see that if gamma is large enough, then your matrix is sparse, because most of the elements are 0. And by decreasing gamma progressively, you can control the sparsity of your Tij. If you send gamma to 0, when gamma is equal to 0, you drop the regularization, and then you get that Tij is going to be the inverse of C, which is, in general, a dense matrix. So it's a dense matrix where all the elements Ij are non-zero because of this noise. Okay? So where should you stop? That's the problem. It's not totally clear where to stop, but what people usually do to choose the right value of gamma is what is called, so the question now is, how do I, so if I add if I add an L1 regularization to my inference problem, I can make the problem, my estimator sparse, so I can get a graph of interactions. But how do I fix gamma? How do I fix the sparsity? Well, what people do usually is what is called cross-validation. So that's a possibility. So you take your data, you split your data in 2 or 3, depends on what you want to do. You can split the data in a train set from which you can compute C, and then you have a validation set, and then you can have a test set if you want to test the result, but let's say you want just to do validation, so you split in 2. The training set is used to compute C, and then you reduce gamma, and you compute the likelihood of the validation set as a function of the t that you infer, right? And if you're lucky, when you plot this as a function of gamma, there will be some maximum, and you can say, okay, the best gamma is the one that maximizes the likelihood of data that I don't use in my training. So basically the idea is that when you are doing, where gamma is too large, you are killing too many elements. Of course, if gamma is infinite, I mean, if gamma is bigger than gamma 1, you are killing everything. So you are underfitting. You have too few parameters. You are not making a good job. When gamma is equal to 0, you have all the possible Tij. So you are going to have L square parameters, and maybe you are overfitting. And if you are lucky, there is a nice maximum in between where you can choose your best gamma. Okay? Yes? In this case? Yes, so what you can do, so the likelihood here is 1/2 log that of t minus 1/2 trace of c times t. Okay? So what you can do is you take your data, y, and you split your data into a training set and a validation set. Okay? From the training set, you compute C training, which is going to be 1/m training times y transpose training y training. So you compute this matrix, and then from this matrix, okay, here you can add the L1 penalty. So you use this, you fix a gamma, you maximize this thing, and you get t. Okay? So this will give a t star of gamma. I forgot to say that this can be done efficiently using some algorithms. I mean, the keyword is graphical lasso. Okay? To maximize this object, there is an algorithm that I don't have time to discuss that is called graphical lasso. So you can efficiently compute the t star that maximizes this thing. And then from the validation data, you compute C validation. Okay? And so from this, now you compute the likelihood as log that t star, the one that you infer from the training data, minus 1/2 times the trace of C validation times t star. And you look as a function of gamma. And again, this is not guaranteed, but if you're lucky, you can have a maximum, and then you say, okay, this is the best. This is the value of gamma that gives the maximum likelihood to the data that I'm not using for my training. So this is the best gamma I can choose. Okay? This is what you always do in cross-validation. You have some parameter that you don't know how to choose. So you split your data in 2. You train on the training set. you compute the likelihood of the validation set, and you look for the parameter that maximizes the, okay. Okay, now, fine. Now, what is the, to have an idea, what is the scale of gamma that I need to choose, okay? So in order to have an idea of the scaling of gamma as a function of the number of data I have, let's look at, so now the question is, what is the scale of gamma versus the number of data I have and the dimension of my problem, okay? So let's look, to have an idea, let's look to a null model. So let's assume that t hat, the true one, ij, is equal to delta ij. So I generate the data with the identity matrix, which means my data, my variables y1, yl, are just IID Gaussians with zero mean and unit variance. So they are all independent, okay? All the components of the vector y are independent. So there is no graph, there is nothing. This is my null model, there is nothing to infer. So I generate m data, and I compute from my m data the matrix Cij. What is the matrix Cij? So the matrix C hat ij, so the true one that I have when the number of data is infinite, is the identity, is the inverse of t hat. The C matrix ij is going to be C hat, so the identity, plus noise, okay? Cij over square root of m, right? So if I take an off-diagonal element of C for I different from j, then the expectation of Cij is equal to 0, and the variance of Cij, which is also the expectation of the square, is going to be 1 over m, where 1 is the variance of z, and if you check the notes of the last week, we had computed the variance of z in general, and if you consider that C hat is the variance of z was like C hat II, C hat jj plus C hat ij squared. So if C hat is the identity, the variance of z is also the identity, so you get 1 over m. So if you have pure noise, then your Cij, the off-diagonal elements of Cij are Gaussian variables with zero mean and variance 1 over m. So then what is the scale of gamma? The gamma, if I put very large gamma, my estimator t is the identity, which is correct in this case. If I reduce gamma, I will start to have non-zero matrix elements in my estimator when gamma is the maximum of C. So this is when I'm starting to fit the noise. So this is when I'm starting to overfit in this case, okay? So what I want to do is to compute the maximum of the Cij, of the off-diagonal, of course. Here it's over I smaller than j. The diagonal elements are 1. So I need the maximum of L. I have L times L minus 1 over 2 variables that are all the possible off-diagonal elements of C, and I want to know the probability of the biggest one. How do I do that? I do this by what is called extreme value statistics. I forgot to say that in this simple case, the Cij are also independent. So I I have L times L minus 1 over 2 variables that are independent and identically distributed with this Gaussian with zero mean. And so what is the probability that the maximum of C is smaller, bigger, depends on, smaller than X? Because they are all independent, the probability that the maximum is smaller than X is equal to the probability that they are all smaller than X, but because they're independent, this is the product of the probabilities. So this will be the product over I smaller than J of the probability that Cij is smaller than X, correct? And because they are all equal, they are all identical, this is the integral between this is going to be the integral between 0 and x over dc, where c of the I need a Gaussian of 0 mean and variance 1 over m, which is this. 2 pi over m. There will be a factor 2 because it's I have to do the maximum of the absolute value, so I want the absolute value smaller than that. Or if you want, I can integrate between minus x and x. See? And because they are all equal, and there are L times L minus 1 over 2 of them, I will have this object to the power L over L minus 1, L times L minus 1 over 2, because they are all identically distributed. So now this is the probability that the maximum is smaller than x. If I want to know the typical value of the maximum, what should I do? I should take, for example, the mode, the median. Okay, so sorry, the median. So the median is the value of x such that the probability of the maximum being smaller than x is 1/2. Okay, so I would like to find the value of x such that this probability is 1/2. This will give me the typical value of this random variable. So this is going to be, I can write this as the exponential of L times L minus 1 over 2. This is the integral of a Gaussian. I know that x is going to be large because I know that if I take the maximum of many things, it will be large. So x is large. This thing is close to 1. So I write it as the exponential of the log of 1 minus the integral between 1 minus twice the integral between x and infinity. Okay, so I use the normalization. So this is 1 minus the integral outside of minus x. And this is small because this is a Gaussian and I'm taking the tails. So this is also, okay, now let's drop the, so we get exponential of L squared over 2 times minus 2 times the integral. And now, this for this now you have to expand the error function. So this is going to be an error function. So you can expand, you can take the asymptotic behavior of this integral, and you get exponential of minus L squared. This thing, when x is large, goes like e to the minus m x squared over 2 divided by x square root of 2 pi m. Okay? So this should be 1/2. So what is the value of x such that this is 1/2? You do the calculation, and what you get is that the maximum, the median of the maximum, let's call it noise, the C noise, the typical value of the maximum, is proportional to 2 square root of log L over M. Okay? So the conclusion is that if I have my null model where I have just noise, as long as gamma is bigger than square root of log L over M, which is my maximum of the Cij, then all the matrix elements of T are 0. And when gamma goes below this value, I start to have non-zero matrix elements, which means I'm fitting the noise. Okay, so this gives you a scale. It's an order of magnitude calculation, but this gives you a scale at which you start fitting the noise, which means you start overfitting. Is it clear? I hope I didn't lose you. Yes?
I think you have to write square of 2 pi divided by n.
No, when you do the asymptotic of this, you get factor 1 over m that gives you plus m here. It's I hope, at least I hope so. I did the calculation yesterday. It should be okay, but yes. Okay. There is time for everyone. So.
Can you also repeat why the 1/2 is the typical value?
Yes, because, okay, these quantities are, so I'm starting with, I'm considering my null model where the Cij should be all 0. But, so if I add infinite data, all these things, this Cij should converge to the identity, and all the off-diagonal elements should be 0. But now I'm saying, okay, because I have noise, because I have a finite number of data, there are spurious matrix elements. And I want to know the maximum. So this is going to be a random variable. So what I did here is say, okay, what is the probability distribution of this maximum? So the standard strategy when you want to do the probability of a maximum of many independent variables is to say, okay, they are independent, so it's a product. And so I get this. Why 1/2? Because this is the cumulative distribution of the maximum. It's the probability that the maximum is smaller than x. So as a function of x, this quantity here is something like this, right? And this will go from, so when you increase the L and M, this will shift to higher values. And 1/2 is the median, is the value of x. This is what I call C noise. This is the value of x such that the probability that C noise is smaller than x is 1/2, and the probability that it's bigger is 1/2. So it's going to be close to the peak of the distribution. So this is an estimate of, so what I want to know is when I increase the size of the problem and I increase the number of data, how does this scale with the parameters? Okay? Okay. Yes?
In this case, we can use the 1/2 because we're using the median, but technically we should look for the mode.
Yes.
Say that in this particular problem, we know that they coincide between the non-equalities.
Yes, but typically these things concentrate, so the median and the mode should scale in the same way with the number.
In this case, it's true because we're doing the null hypothesis with the identity correlation.
Yes, because I'm doing this because I can apply extreme value statistics. If my data are, if I am in a more complicated case, then I don't know, but yes.
L is the number of non-zero elements in C. What is L?
L? Sorry, L is the size of your problem. So my data are vectors of size L. And M is the number of vectors I have. So for example, if you're looking at proteins, L will be the length of the proteins. So each site is one amino acid, and it will be a number. So you have L numbers. And M is the number of data you have, so how many sequences you have. Okay?
Excuse me.
Yes?
I didn't understand
C noise is the value of x such that the probability that the maximum C is smaller than x is 1/2. So if you want, C noise is the typical value of the maximum. So you have this matrix Cij that should be 0 of diagonal. Because of noise, it is non-zero. I want to look at the biggest matrix element, and C noise is the biggest matrix element, which is random. But by this argument, I'm saying it's a random number, but of the order of this thing. Okay?
So, why you take common 1/2 of C noise and not
Oh, no, sorry. It's just an order of magnitude, so the prefactors were, the two should be there.
Explain what is x here?
X?
Yes.
X is any real number. I take a real number x.
So can we replace it by gamma?
No. Gamma. So what am I doing is I have data. I fix. Now I want to infer t, given my data. So from the data I compute c. Then I choose a gamma. This is my choice. I choose a gamma, and I get a t. If gamma is bigger than this, then t is the identity, which means in my example, in my null model, that I'm not overfitting. If gamma is smaller than this, I start overfitting. This is gamma. Now I forget about gamma, and I want to know how big is this number as a function of how many data I have. So this argument here is I want to know the probability distribution of this random number. The probability distribution of this random number, the cumulative, is going to be something like this. And I want to know, ideally I would like to know the mode, but I say, okay, I get the median, so let's look at the median. The median is the value of x such that this function is equal to 1/2. I do this calculation and I get that x, which I call C noise, is this. So my conclusion, is it okay? Any other questions? Yes?
I would have expected gamma to depend on the signal to noise ratio.
Yes, but here there is no signal. Here is pure noise. I'm looking to the case where there is no signal. So yeah, I agree. I mean, the point is how big is the signal with respect to this noise. Here I'm just estimating the order of magnitude of the noise. So it's really it's an argument. It's not the. So let me finish and then we can discuss this. I agree. So sure.
What should we put on the y-axis of that graph?
Here, this function f, which is the cumulative distribution of this quantity. So this is a random variable. I call f of x the probability that this random variable is smaller than x, and I want to find x such that this is 1/2. So I first compute f of x, and then I found x such that this is 1/2, and this gives me the median. Okay? So
I want x such that f.
yes, exactly. So the conclusion of the argument, which I insist is just an argument, is not a theorem, then later I will give you a more precise result. But the conclusion of this is that if I have pure noise, if gamma is bigger than this, I'm okay. I get the correct result, which means I get the identity. If gamma is smaller, then I start fitting the noise. Why I spent time on this? Because this is interesting. It tells you that in order to start distinguishing the noise, you need m to be of the order of log L. So you see that this ratio depends on the ratio of log L with m. So you need few data. So L is the size of your problem. You have L parameters. Here you have L square parameters, the matrix. But anyway, L is the size of your problem, how many components you have in your data. And this is telling you that you need of the order of log L data to realize that there is no correlation in the data, okay? So the biggest matrix element, if you have pure noise, is of the order of log L over M, which has to be compared with, you remember last week, I told you that in order to do PCA, so in order to infer the principal component of your data, you need of the order of L data. So you see, I mean, if L is 1,000 or 100, which is the size of a typical protein, then log L is a small number. With few data, you can realize that if there is noise, the noise goes away. But if you want to compute the principal components of T, you need much more data. You need of the order of L data. Why? Because the problem is that once again, Cij is the true one plus a number of order 1 divided by square root of M. So now maybe this comes to your question. So if I have a signal, this is small enough that I can, so if I know if my matrix is sparse, most elements are 0, and there are only a few that are non-zero, getting the ones that are non-zero is not that hard, because this is 1 over square root of M. So if there is a signal, this signal is going to be in the noise, but the noise is 1 over square root of M, and because there are L square elements, the biggest one is square root of log L over M. So as long as M is much bigger than log L, I can get rid of the noise and I can infer which ones are the non-zero elements. But if I want to get the principal components, these depend on all the matrix elements, and as I showed you last week, this small noise can accumulate, and you need M to be, let's say, bigger than, or much bigger than L in order to be sure that the eigenvalues of C coincide with the eigenvalues of C hat, and so you can infer the principal components in your data. Okay, so there is a difference between the problem of understanding which ones are the non-zero interactions, if you know that the problem is sparse, which is easier than getting the principal components of the matrix if you have a dense matrix. Okay? Is it good up to this point? Yes?
You got these scales with L1 regularization.
Yes.
With L2.
Yeah, exactly. So this depends on the regularization. So the problem is, okay, L1 is tractable, so you can get this. With L2, I think you don't really, it doesn't really get sparse, because L2, the term that you add is small when T is small. So if you can show that you can solve it, and you can see that the matrix is just not sparse. So you don't have this property of L1. The good property of L1 is that when gamma is large enough, it kills everything, and then one by one they appear, which is not the case in L2. So in L2 you cannot do this. And if you do L0 or other things, then it's non-convex. You cannot really make an argument like this. So I don't know the answer to this question. Okay. Now let me make this statement more precise now, okay? This was just an argument. So to make this statement a bit more precise, I want to introduce a last idea, which is what is called pseudo-likelihood maximization. So again, we will stay for the moment in the world of Gaussian variables. So So instead, now the idea of pseudo-likelihood maximization is, okay, we want to know the conditional probability. Let's work with the conditional probability. So I said before, what I want is the probability of yi given the other variables and t. And this was, I wrote it as square root of t over 2 times the exponential of minus t over 2 times y minus sum over j different from y, from I of t ij, sorry, no hat, no, square. So let's suppose that my data have been generated by a multivariate Gaussian with some t hat that I don't know. I don't know the t hat, but I know that the variables are Gaussian. So if the variables are Gaussian, this is the conditional probability. Can I try to learn the t directly from this without going through the total likelihood? The total likelihood is the multivariate Gaussian. This is what I did before. I can do this. So I can write what is called the pseudo likelihood of the data given t, which is just 1 over m times the sum over m of the logarithm of this quantity. What do I get? Well, what I get is 1/2 log of tii, which comes from the normalization. When I take the log, I get 1/2 log t. I average over the data, but it doesn't depend on the data, so I just get this, minus. When I take the log of this, I get tii over 2 times a function g that depends on the data and a vector ti. What is this function? Sorry. Well, yeah, ti. What is this function g is the average of this square, right? When I take the log, I get minus ti over 2 times the average over the data of this. So g is 1 over m times the sum over the data of yim minus the sum over j different from I of t ij times yjm square. And this t ij is given by tij divided by tii. Okay? So I took the log. I average over the data. The first term is a constant. The second term is minus ti over 2 times the average of this that I call g. And so this is the average of the square over the data. And I call this ti. Okay? So you see, and this is a general property of pseudo likelihood, that when you write the pseudo likelihood, it doesn't depend on the full matrix T, but it only depends on this, on the elements Tij, where I now is fixed, right? So if you have your matrix Tij, this will only depend on one row. So if you do the pseudo likelihood for variable 1, it depends on T1j, and then T2j, and so on and so forth. So what you do when you do pseudo likelihood is that you infer each row independently from the conditional probability. Okay? Now, let's write T. So Ti is the vector that contains T1, 1, well, okay, So it will be basically Tij over Tii. Okay, for j going from 1 to L. So I have to repeat this thing for each I, and I will get each row of the matrix T, and then I put everything together. Okay. This object here is easy to compute. If you take the square, if you develop the square, you get yi square average, which is Cii, and then you get plus 2 sum over j of Cij Tj, and then I get this, and then you get the square of this, which is plus sum over jk different from I of Cjk Tj Tk. So this G is a quadratic form of the T. Now you see the Tii, I mean the one with j equal to I is equal to 1. So you only have the Tj for j different than I. This is a quadratic form. You can optimize, and you get your estimator T star I, T star, let's say the vector T star, which is given by, okay, let's write it in this way, T star I component j is equal to minus the inverse of this matrix times C times this one, right? So you have to invert the, when you take the derivative, you set the derivative to 0, you invert, and you get this. It's not very important. The formula is not very important. What I want to stress now is the following thing, and I will not do the calculation because otherwise it's too many calculations for today, but you have a few results that are interesting. So the first is, okay, so sorry, in order to get your estimate, you minimize this. Sorry, you maximize because you have a minus sign, but okay, you maximize this, you get T star, and then from the expression I just erased, you also get the diagonal elements.
I missed why we call that matrix CR.
Ah, sorry, no, this is CR. It's R because it's the reduce. You see, this is the matrix Cjk. So you have your matrix C, and you have to remove the line and column I to get Cjk for jk different than I, and this you call this CR. So this is a L minus 1 times L minus 1 matrix that you have to invert. You invert it, and you apply it to the vector Cij, which is the vector that corresponds to the row here. Okay? So you take your matrix C, you remove one line and one column, you get a reduced matrix, you invert, you apply to this, and you get your T. Okay, the important results are the following. First of all, when m goes to infinity, you can prove from this that T star ij that you get from pseudo likelihood maximization, so from this, converges to the true T, which is not trivial, okay, because here you are doing a maximization on each line separately, and it's not guaranteed that it should converge to the ground truth. So you can analyze this expression, and you can see that if you have infinite data, it works. You get the right result. So it's a consistent estimator of T hat. So if you have infinite data, it works as well as maximum likelihood. You can do the one you prefer. The problem is that if m is finite, because here you are inferring each line of T separately from the others, you are not sure that T, you don't have a guarantee that T is symmetric. So in general, you might have asymmetric matrices. So then you don't know, I mean, so you know that the original matrix is symmetric, so which one you believe, then you have to decide. You could take the average or something like this. So pseudo-likelihood maximization is a good way of doing things, but it will give you, if you have many data, it will give you the correct result, but if you have few data, you can have trouble in interpreting the result because it will give you different matrix elements while they should be the same. Okay, so again, what is this? How many data you need to decide? So, yes.
What is the advantage of this likelihood maximization? The calculations are easier?
So in the Gaussian case, not really. In the Gaussian case, they are essentially the same. But we will see next that in more in non-Gaussian cases, this is much easier to do. But the reason why I'm doing it now is that there is a result. So I wanted to show one precise result that you can have for this pseudo-likelihood maximization. So let me say it, and then we can come back to this afternoon. We can come back to why this is easier in general. So there is a result that says the following thing. So suppose I add now an L1 regularization. So if you add an L1 regularization, then G, so the off-diagonal elements are here, are these T. Okay, these are the off-diagonal elements. So let's add a penalty. The penalty is with the plus sign because I erased it, but the pseudo-likelihood was equal to, of the I element, was equal to 1/2 log T minus T over 2 times G. Okay? So,
Can you repeat really briefly what was G?
yes.
What?
So I compute the pseudo-likelihood, which means this is my conditional probability. I take the log, and I average the log over the data. And this is my pseudo-likelihood. Okay? When I take the log and I take the average, I get the log of this, which is a constant. So you average a constant and you get this. And then I get minus T over 2 times the average of this. And the average of this, I call it G. So G is the average over the data of the term in square. And then I say, okay, in order to get my best estimator for the T, I have to maximize this. So the diagonal element is here, but the diagonal element is fine. It's not, this is going to be essentially of order 1, the diagonal elements. So the off-diagonal elements that are the one I'm interested in if I want to know the graph of interactions. So the off-diagonal elements appear in G. So maximizing this, because there is a minus sign and this is a definite, positive definite matrix, maximizing this means minimizing G. So I want to minimize G. So if I want to regularize the problem, I have to add the penalty for non-zero T. So I put a plus gamma because I have to minimize G. Okay. So now, if I add the regularization, then there is a result. Now I will, this is a, there is a theorem that it's that I will not give in the proper form, but essentially the message of the theorem, this is a theorem by Schausen and Pullman. It's cited in our book, so you can find the reference there. Paper from 2006 that says that if M is much bigger than log L, and you choose gamma here to be of the order or bigger than square root of log L over M, so this is the result I got before, then I mean the theorem is a bit more complicated, but essentially it says this. If you have this, then you from the pseudo likelihood maximization estimator, then you can recover you can recover the entries of t hat bigger than 1 over square root of m with very high probability. Okay, which means, okay, here this is random because you have random, so you have a true t. Let's assume that this true t has some big entries that correspond to strong interactions and the rest are either 0 or very small. Now from this true t you generate data. You don't have many data, but you have enough data, much more than logarithm of L. So if you have enough data, your C is going to be noisy, so the data are noisy, but still, if you regularize and you maximize the pseudo likelihood, you get an estimator for t hat, and with very high probability over the noise, the entries of t hat that are bigger than 1 over square root of m will be identified by your estimator, okay? So this should also, again, this is now here the signal should be bigger than 1 over square root of m, and the data should be enough, and then you are fine, okay? You can recover your interactions, okay?
I didn't understand what in this case we are analyzing the non-zero value of Tj. Because here we didn't assume that the true matrix is diagonal.
No, exactly. So here I'm assuming that the true matrix is sparse. So before I was doing a null model, I was saying, okay, I have pure noise, and I was trying to estimate how much regularization I need to kill the noise. Now this is a stronger result. Now I'm saying, okay, my matrix T hat is sparse, so there are some non-zero entries, but they are few, and many others are 0. And the question is, can I get the signal now? Now there is a signal, so can I get the signal? And the answer is yes, I can recover the non-zero entries with a high probability, provided that the non-zero entries are big enough, so there is a signal, and I have enough data, and I choose my regularization wisely, okay? So this is the content of this theorem, which holds for pseudo likelihood with L1 regularization. So unfortunately, it's not the fully general setting, but at least you get an insight.
And what about the other entries? Will they be 0 or just noisy?
I think they will be noisy. Some will be 0, some will be noisy. I mean, as usual with L1, you have many entries that are 0, but some will be noisy. Then it. Okay. So we did now all we could do with Gaussian variables, and now the next step is to go to more general situations. But I would say maybe we can do this afternoon, and for the moment we can stop here. So what I want to do next is to discuss the case of discrete variables. We will see how we can define graphical models for discrete variables and how we can infer them. And then, and we will discuss regularization also in that case. And then what I would like to do is to show you an application to proteins that will take the next tomorrow and the day after tomorrow, I think. Maybe we can start today, but and I will conclude with this. So if there are no questions, we can go to lunch. But if you have questions, I'm happy to take them.
Can I ask how the exam is going to be?
Oh, right, the exam. I didn't prepare it. It's the first time I do this, so I have no idea. I was thinking to do something similar to what was done by Mauro Pastore and Bruno Loureiro, but maybe, I mean, I'm not sure I will be able to reach this level of detail. So it will be basically questions with multiple answers, and you have to choose an answer. But I think looking at that, it looks a lot of material, so I'm not sure I can prepare that much. So I don't know. It's going to be something, basically questions on what I said. I would say multiple choices, and the question will be on things, on what I said in the lectures. So not, I mean, you don't have to, it's only on what I said during the lectures, not more than that, okay?